Welcome to Chapter 2 of Principles of Mathematical Analysis. In this section, we study metric spaces, which provide the natural setting for discussing limits, continuity, and convergence. A metric space is simply a set equipped with a notion of distance. This abstraction lets us do analysis not just on the real line, but in much more general settings. Here is an outline of what we will cover. We begin by defining metric spaces and looking at key examples. Then we introduce the fundamental topological concepts: neighborhoods, limit points, open sets, closed sets, and more. After that, we prove the basic theorems about open and closed sets, including De Morgan's laws and closure properties under unions and intersections. Finally, we discuss the closure of a set and the notion of relative topology. Let us define the central object of this section. A metric space is a set equipped with a distance function satisfying certain axioms. The first axiom, positivity, is what prevents the notion of distance from being trivial. Without it, two different points could have distance 0, and we would lose the ability to distinguish them metrically. Notice that the axiom has two parts. Distinct points must have strictly positive distance, and the distance from any point to itself must be 0. This second part is a normalization. Next, we see another fundamental property. Symmetry says the distance from P to Q is the same as from Q to P. This might seem obvious, but there are useful asymmetric notions of distance, such as travel time on one-way streets, that do not satisfy this axiom. By requiring symmetry, we ensure that distance behaves like our geometric intuition of length. The third property, the triangle inequality, is the most powerful of the three. The third property is the triangle inequality. It says that going from P to Q directly is never longer than going from P to some intermediate point R, and then from R to Q. This is the most substantial of the three axioms and plays a crucial role in many proofs. A function satisfying all three properties is called a distance function, or a metric. As you can see, the direct path from P to Q is never longer than the detour through R. The triangle inequality is the workhorse of metric space theory. Almost every proof in this chapter uses it at some point. It is what makes neighborhoods well-behaved and allows us to control distances indirectly. Interestingly, equality holds in Euclidean space precisely when R lies on the line segment between P and Q. Euclidean spaces are by far the most important examples, and they are the setting for most of classical analysis. Verifying the triangle inequality for Euclidean distance is actually the hard part. That is what Theorem 1.37 from Chapter 1 established using the Schwarz inequality. It is worth noting that the Euclidean metric is not the only way to measure distance in R to the k. For instance, the maximum of the coordinate differences also defines a valid metric, but we will mostly work with the standard Euclidean one. Now let us see an important observation about subsets. Here is a crucial observation. Every subset of a metric space is automatically a metric space in its own right, using the same distance function. If the metric axioms hold for all points in X, they certainly hold when we restrict to a subset Y. This means every subset of a Euclidean space is a metric space. This observation will become very important later when we discuss relative topology. Rudin introduces several geometric objects that will appear throughout the book. The distinction between segments and intervals is important. Segments exclude endpoints, intervals include them. This seemingly small difference has major topological consequences. A segment is an open set, while an interval is closed. Half-open intervals, which include one endpoint but not the other, are neither open nor closed. These will serve as our go-to examples when testing topological definitions. Next, we generalize to higher dimensions. A K-cell is the higher dimensional generalization of a closed interval. It is the set of all points in R to the K, whose coordinates each lie within specified bounds. On the left, you can see a 1-cell, which is just a closed interval on the real line from A1 to B1. On the right is a 2-cell, which is a rectangle in the plane. Each coordinate x1 ranges from A1 to B1, and x2 ranges from A2 to B2. A 3-cell would be a rectangular box in 3-dimensional space, and so on for higher dimensions. We now turn to another fundamental geometric concept. Open and closed balls generalize segments and intervals to any dimension. The key distinction is whether boundary points are included. This matters because open balls are the building blocks of all topological concepts in metric spaces. Neighborhoods, open sets, continuity, and convergence are all defined in terms of open balls. In R1, an open ball is just a segment. In R2, it is an open disk. In higher dimensions, the shape depends on the metric, but the concept is the same. Next, we introduce an important geometric property. A set is convex if for any 2 points in the set, the entire line segment connecting them also lies in the set. Balls and K-cells are both convex, as one can verify using the triangle inequality for balls and the definition of K-cells. Let us look at a diagram to see the difference between convex and non-convex sets. On the left, we have a convex set. Any 2 points, x and y, inside the set can be connected by a line segment that stays entirely within the set. On the right, we have a non-convex set. The points x and y both belong to the set, but the line segment between them passes through a region outside the set. That single violation is enough to make the set non-convex. We now introduce the most important collection of definitions in this section. These definitions form the vocabulary of topology. A neighborhood of a point P is simply an open ball centered at P with some positive radius r. It contains all points whose distance from P is strictly less than r. In the real line, neighborhoods are open segments. In the plane, neighborhoods are open disks. Next, we define when points accumulate near boundaries of sets. A limit point of a set E is a point P such that every neighborhood of P, no matter how small, contains at least one point of E different from P. The points of E crowd around P. Note that P itself does not have to belong to E. An isolated point is the opposite. It belongs to E, but some neighborhood of it contains no other points of E. It sits alone, separated from the rest of the set. Now, we define properties based on limit points and interiors. A crucial subtlety here: open and closed are not opposites. A set can be both open and closed, like the whole space X or the empty set. A set can also be neither, like a half-open interval. Think of closed as meaning the set traps its limit points. You cannot escape by approaching the boundary. Open means every point has breathing room. These are independent properties that happen to be linked through complements, as we will see in Theorem 2.3. We now introduce the complement and a special type of closed set. The complement of E is the set of all points in X that do not belong to E. A set is perfect if it is closed and has no isolated points. Well, that means it contains all its limit points, and every point in it is a limit point. So a perfect set has a very uniform structure. Every point is crowded by other points of the set, and nothing is missing from the boundary. A closed interval, like the set of all x between 0 and 1, is a simple example of a perfect set. Finally, we define the remaining topological properties. A set is bounded if it can be contained within some large ball. There is a single ball big enough to hold all of E. A set is dense in X if it comes arbitrarily close to every point of X. The rationals are dense in the reals, for example, because between any two real numbers there is a rational. This completes our topological vocabulary. These 10 definitions are the building blocks for everything that follows in this chapter. Our first theorem says that neighborhoods, which we defined as open balls, are indeed open sets in the sense of definition 2b-18. This is reassuring. The terminology is consistent. Let us prove this. The proof uses the triangle inequality. Take any point Q in the neighborhood of P with radius r. The distance from P to Q is less than r, so there is a positive gap, h, equal to r minus that distance. We claim the smaller neighborhood of Q with radius h fits entirely inside the original neighborhood. For any point S within distance h of Q, the triangle inequality gives us that the distance from P to S is less than r. Let us look at a diagram to see this visually. The diagram makes the geometry clear. The key insight is how we chose the radius h of the green ball. It equals exactly the gap between Q and the boundary of the blue ball. This guarantees the green ball cannot poke outside the blue one. This technique of choosing a radius equal to the remaining gap appears repeatedly in topology proofs. Whenever you need to show a point is interior, you compute how much room is left and use that as the radius of a smaller neighborhood. This theorem strengthens the definition of a limit point. The definition only requires that every neighborhood of P contains at least one point of E different from P. But the theorem says that if even one such point exists in every neighborhood, then in fact, infinitely many must exist. Let us see why. The proof is a clever contradiction argument. If some neighborhood of P contained only finitely many points of E other than P, we could take the minimum of the distances from P to each of these finitely many points. This minimum is positive because there are only finitely many points. A neighborhood of P with this smaller radius would then contain no point of E other than P, contradicting the assumption that P is a limit point. The corollary follows immediately. If E is finite, no point can have infinitely many points of E nearby, so there are no limit points. Concrete examples are the best way to build intuition for these abstract definitions. As we go through these 7 subsets of R2, pay attention to how properties like open, closed, and perfect interact. You will see that some familiar sets have surprising properties, and that seemingly simple sets can behave differently depending on the ambient space. Now we examine more examples. Set D is the integers. Set E is the sequence of reciprocals, 1, 1 to 2, 1 to 3, and so on. This set has an interesting property. 0 is a limit point of E. because the reciprocals get arbitrarily close to 0, but 0 itself is not in E. This illustrates the distinction between having a limit point and containing it. Set F is the entire plane, and set G is an open segment on the real line. Let us now summarize the properties of all these sets in a table. This table summarizes the properties of each set. Notice some interesting points. The entire space, set F, is both open and closed. That might seem contradictory, but it is perfectly consistent with the definitions. The segment in G is open as a subset of R1, but not as a subset of R2. This shows that topological properties depend on the ambient space, which motivates the concept of relative topology that we will discuss later. This is De Morgan's law for sets. The complement of a union is the intersection of the complements. This purely set-theoretic result will be the key tool for transferring results about open sets to closed sets and vice versa throughout this chapter. To show two sets are equal, we show each is a subset of the other. For the first direction, take any x in A, the complement of the union. Then x is not in the union, which means x is not in any of the individual sets E alpha. So x belongs to the complement of every E alpha, which puts x in the intersection of all these complements, namely B. This gives us A is a subset of B. For the reverse direction, take any he x in B, the intersection of the complements. Then x is in the complement of every E alpha, meaning x is not in any E alpha. So x is not in the union, which means x belongs to the complement of the union, namely A. Since we have shown both A subset B and B subset A, the two sets are equal, and the proof is complete. This theorem reveals the fundamental duality between open and closed sets. A set is open precisely when its complement is closed, and vice versa. This means we can always translate a statement about open sets into one about closed sets by taking complements. The corollary is immediate. By applying the theorem to the complement, let us prove the forward direction. The proof strategy is elegant. We translate openness of E into a statement about the complement being closed. Take any x in E. Since x is not in the complement, and the complement is closed, meaning it already contains all its limit points, x cannot be a limit point of the complement either. This is where closedness does the heavy lifting. We extract the key consequence. Here is the crucial logical step. Not being a limit point of the complement means there is some neighborhood that avoids the complement entirely, and a neighborhood that avoids the complement must lie entirely inside E. This is the bridge between limit points and interior points, two concepts that at first seem unrelated. Since x was arbitrary, every point of E is interior, so E is open. Notice how the proof never directly computed neighborhoods or distances. Instead, it worked purely through logical relationships between limit points, complements, and interior points. This style of proof is typical in topology. Now let us prove the reverse direction. For the reverse direction, suppose E is open and x is a limit point of the complement. Then every neighborhood of x contains a point of the complement, which means no neighborhood of x is entirely contained in E. So x is not an interior point of E. We now conclude the proof. But E is open, meaning every point of E is interior. Since x is not interior, x cannot be in E, so x must be in the complement. We have shown that every limit point of the complement lies in the complement, which means the complement is closed. This completes the proof of Theorem 2.23. Theorem 224 tells us how open and closed sets behave under unions and intersections. Part A says that any union of open sets is open, no matter how many sets are in the collection. This is because if a point belongs to the union, it belongs to at least one of the open sets, and so it has a neighborhood inside that set, hence inside the union. Part B is the dual statement. Any intersection of closed sets is closed. This follows from Part A by taking complements and applying De Morgan's law. The complement of the intersection of closed sets is the union of their complements, which are open, and that union is open by Part A. So the intersection is closed. Part C requires finiteness. A finite intersection of open sets is open. The proof takes the minimum of the radii of the neighborhoods at a given point, one for each open set. Because there are only finitely many, the minimum is still positive. This gives a neighborhood that fits inside all of the sets simultaneously. Part D completes the pattern. Part D is the dual of Part C. A finite union of closed sets is closed. Again, this follows from C by complementation. Notice the pattern. Unions preserve openness, intersections preserve closedness, and for the reverse operations we need finiteness. Let us now see why finiteness is essential. The proof of Part A is beautifully simple. The key observation is that to show a point is interior to the union. We only need it to be interior to one member of the union. We do not need a neighborhood that fits inside all the sets at once, just one of them. That is why no finiteness assumption is needed here. We complete the argument. Since G alpha is a subset of the union G, the neighborhood that fits inside G alpha automatically fits inside G. Compare this with the intersection case, where we need to fit inside every set simultaneously. That difference is exactly why intersections require finiteness. Let us see that proof next. For the finite intersection, take any point x in the intersection H. Since x belongs to each of the n open sets, for each g I, there exists a neighborhood of x with some radius r I that fits inside g I. Now we use the finiteness assumption. Now take the smallest of these n radii. Because there are only finitely many, and each is positive, the minimum r is still positive. This is exactly where finiteness is needed. An infinite minimum of positive numbers could be 0. We conclude by showing the intersection is open. The neighborhood of Ex with this minimum radius fits inside every one of the n sets, hence inside their intersection H. So X is an interior point of H, and since X was arbitrary, H is open. Parts B and D follow from A and C by taking complements and applying De Morgan's law. This example shows why finiteness cannot be dropped from parts C and D of Theorem 2.24. Each interval from -1 over n to 1 over n is open, but as n grows, these intervals shrink toward 0. Their intersection is just the single point 0, which is not open, so an infinite intersection of open sets need not be open. Similarly, an infinite union of closed sets need not be closed. Now we turn to the closure of sets. The closure of a set E is formed by taking E and adding all its limit points. The notation is E bar. Think of it as plugging all the holes in the boundary of E. For instance, if E is an open disk, its closure is the closed disk. We add all the boundary points, which are the limit points not already in E. The closure is the smallest closed set containing E, as we will see next. Theorem 227 establishes the three key properties of closure. Part A says the closure is always a closed set. This is what we would hope. After adding all limit points, there should be no more limit points missing. Part B characterizes when closure is unnecessary. Part B says that a set equals its own closure precisely when it is already closed. This makes perfect sense. A closed set already contains all its limit points, so adding them changes nothing. Conversely, if adding limit points does not change the set, then it must have contained them all along. Part C gives us a minimality property. Part C says the closure is contained in every closed set that contains E. Combined with Part A, this means the closure is the smallest closed set containing E. It is the most efficient way to close up E. Now, let us look at the proofs. For Part A, take a point P not in the closure. Then P is neither in E nor a limit point of E. Since P is not a limit point, some neighborhood of P avoids E entirely. But then it also avoids the closure. This means the complement of the closure is open. So the closure is closed by Theorem 2.23. Part B is next. Part B gives a useful test for closedness. Just check whether the set equals its closure. If adding limit points changes nothing, the set was already closed. This is often the most practical way to verify a set is closed in proofs. Part C establishes a minimality property. For Part C, if F is closed and contains E, we use two facts. First, since E is a subset of F, every limit point of E is also a limit point of F, so E prime is a subset of F prime. Second, since F is closed, F contains all its own limit points, so F prime is a subset of F. Combining these, E prime is a subset of F, so F contains both E and the limit points of E, which means F contains the closure of E. This completes all three parts of the theorem. This theorem connects the supremum from Chapter 1 with the closure from topology. It says the supremum of a bounded above set of reals always belongs to the closure of that set. If the set is closed, the supremum is actually in the set. This is a useful and intuitive result. The least upper bound is either in the set or is a limit point of the set. Let us prove this. If the supremum y is already in E, then it is certainly in the closure, and we are done. The interesting case is when y is not in E. We claim that for every positive h, there must be a point x in E strictly between y minus h and y. Why is this true? We explain the key observation. If no such x existed, then every element of E would be at most y minus h, making y minus h an upper bound of E. But y is the least upper bound, so no smaller number can be an upper bound. This is a contradiction, so such an x must exist. We now conclude. Since this holds for every positive h, every neighborhood of y contains a point of E. This makes y a limit point of E, so y belongs to E prime and hence to the closure. As the diagram shows, no matter how small a neighborhood we take around Dillon y, there is always a point x of E inside it. This remark introduces relative topology. When we ask whether a set is open, the answer can depend on the ambient space. A set E inside a subspace Y is open relative to Y if every point of E has a neighborhood restricted to Y that stays within E. As we saw in example 2.21, the segment from A to B is open when viewed as a subset of the real line, but not when viewed as a subset of the plane. The next theorem gives a clean characterization of this concept. Let us see it. This is an elegant characterization. A set is open relative to Y if and only if it is the intersection of Y with some set that is open in the full space, X. So relative openness is not a mysterious new concept. It always comes from restricting an open set in the ambient space to the subspace. Let us prove both directions. First, the forward direction. Here is a concrete picture. Take X to be the entire plane and Y to be the real line sitting inside it. The segment E from A to B is open relative to Y, meaning every point in E has a small interval around it that stays inside E. Now look at the dashed blue region G, which is an open disk in the full plane. Notice that the intersection of G with the line Y gives exactly. That is the content of theorem 2.30. Every relatively open set arises as the trace of some open set in the ambient space. Conversely, any such intersection is relatively open. Let us now prove this formally. For the forward direction, since E is open relative to Y, for each point P in E, we have a radius r sub P such that any point of Y within that radius belongs to E. We form the open ball V sub P in the full space X and take the union of all these balls. This union G is open in X by theorems 2.19 and 2.24. Now we need to show that E equals G intersected with Y. We verify both inclusions. First, every point P in E lies in its own ball V sub P, hence in G, and P is in Y. So E is a subset of G intersect Y. Conversely, any point Q in G intersect Y belongs to some V sub P and to Y. So by the choice of R sub P, Q is in E. Therefore E equals G intersect Y. Now let us prove the converse direction. The converse is more straightforward. If we already have E as the intersection of Y with an open set G in the full space, we just need to show points of E have relative neighborhoods inside E. Since G is open in X, each point of E has a full neighborhood inside G. We restrict to Y to finish. Restricting to Y gives us that V sub P intersected with Y lies inside G intersected with Y, which is E. So the relative neighborhood condition is satisfied. The beauty of this theorem is that it reduces the relative topology on Y to a simple intersection operation. You do not need to rederive open sets from scratch in the subspace. You just slice open sets from the ambient space with Y. Let us review the main ideas from this section. We started by defining metric spaces as sets equipped with a distance function, satisfying three natural axioms. Euclidean spaces are the primary examples. Next, we introduced fundamental topological concepts. We then introduced the fundamental topological vocabulary: neighborhoods, limit points, isolated points, open and closed sets, interior points, complements, boundedness, density, and perfectness. These 10 concepts are the foundation for everything in this chapter. Then we proved key properties about these sets. we proved the fundamental duality between open and closed sets via complements, and established the union and intersection rules. A key subtlety is that finiteness is required for intersections of open sets and unions of closed sets. Next, we discussed closure. Finally, we defined the closure as the set together with its limit points, proved it is the smallest closed set containing the original set, and characterized relatively open sets as intersections of a subspace with an open set in the ambient space. In the next section, we will study compact sets, which introduce a powerful finiteness condition that has far-reaching consequences throughout analysis. See you there.